Okay, 12 o'clock. Okay, here we go.
I haven't looked on the website to see what they're saying.
Hello.
Hello.
Hey, Google, stop.
Yeah, that. Why? There's no trapezoid. How's on trapezoid? That thing's.
Welcome, everyone.
Hello, everybody. How's everybody doing? Hey, welcome to Destination Space 2021. Remember, this month in March, we're going to the moon. Okay, we're already on the 4th week of March. And so far, we told you about our moon program. We told you about our big rocket. We had an educator in space, an astronaut, a teacher that went to space. And then we had Lindsay Aitchison, who told us about the new astronaut suits. We also talked about the new habitats or the houses we're gonna be building in space. We told you about the Gateway, a spaceship that we're gonna place orbiting the moon. And then last week, Mr. Stu McClung came and told us about the new Orion spaceship, our spacecraft that's gonna take the astronauts to the moon. Mr. Andres Marquez talked to us about virtual and augmented reality. And then Dr. Tony Colapri told us about the Viper mission. He's gonna be hunting for water on the moon. He told us all about all of the water that's on the moon. And then yesterday, Mr. Nanteo Suzuki told us about the human landing systems, the spacecrafts that we're gonna use to get our astronauts to the surface of the moon. Today, we have another special guest. Today, we have Dr. Sergio Santamaria. And Dr. Santamaria is currently the lead scientist for the BioSentinel mission. It's a mission where we're gonna use a small spacecraft, a small satellite, and we're gonna be taking biology and we're gonna be conducting an investigation on the biological response to DNA damage and the different mechanisms used to repair damage for almost 20 years. He has worked with us for a number of years, and today he's going to be talking about this really cool mission. I think it's really cool and important mission for human exploration. This is one of my missions, and I'm really happy that Dr. Santamaria, Dr. Sergio Santamaria is with us today. Dr. Santamaria, thank you for joining us today.
Of course. So I'll go ahead and share my screen. How is everybody doing? It's a nice day outside so far.
I forgot to mention our only rule. Everyone, remember, we have to keep our mics muted, okay? So that Dr. Santamaria can share with us all the incredible work that he does for us at NASA. All right, thanks.
All right, you guys can see the slides. So I'm Sergio. I'm actually was born in Peru. I came from Lima, Peru in South America many years ago to do my research and my studies here in Texas, then in New York, New Jersey, and now in California. And I came to California to work in this particular mission, which is a pretty cool mission. It's the first time we're sending actual biology, something alive, on purpose, of course, to interplanetary space. As you know, sometimes some microbes, some bugs get attached to the rovers, not on purpose, of course, but in this case, we're actually sending them on purpose to study how they respond to the deep space environment. I actually took this picture, so I'm very proud of the moon there. You might have heard a lot about the NASA journey to Mars and how the Artemis program is so important to achieve that goal in the next 15, 20 years. And the mission that I work on actually is part of the Artemis program to some degree. It's actually one of the first biological mission selected as part of the Artemis program. And so what do we care about sending biology? You know, the idea we want to send astronauts, of course. However, we have very little information on what happens to humans in deep space. What I mean by deep space is you don't know, our Earth, our planet, is protected by a magnetic field. It's like we have a sphere, a ball around Earth that protects us from radiation. And the only time we have left this magnetic field or ball is when the Apollo astronauts went to the lunar orbit or the surface of the moon many years ago, the last one in 1972, so almost 50 years ago. But now that we're planning potentially, to go back to the moon and stay there as part of Artemis, or even going to Mars later on, these are significantly longer missions. And we really want to know what could happen to biology without sending the astronauts first. And that's when a mission like BioSentinel comes in. So I put here this graph, and you can see at the bottom left, all that highlighted in green is what we know the most, right? We know what happens on the International Space Station, or what could happen to biology there. We have suborbital flights, and we also have some experiments on the moon. However, we have not done anything outside of that. Everything that we send outside this moon Earth system has to do with robotic missions. We have the famous Mars rovers, a lot of missions going to Pluto and other planetary bodies, even to the sun, right? But we don't know what happens to biology there. We can just guess. It's very an educated guess. So what are the main things that happen to biology? One of them, as you might have heard, is microgravity. So you see one of the Kelly twin, the astronauts, playing with a ball of water in space that's produced because reduction in the gravity. And just imagine your bodies, your organs, everything you have being in this environment, which can have significant effects. One of the main things that happen to astronauts is they actually lose muscle. They even lose bone. They get disoriented. They can have effects even in their hearts. Just like in humans, microorganisms like bacteria and fungi and little critters like flies and so on, they also have other effects. One of the most well-known studies is with microbes, is that they become worse. Meaning they become more aggressive in space. Some viruses actually get activated faster in space as well. In the case of plants, there's some issues with the way they grow. And NASA has been leading the effort together with our partners around the world to develop technologies to study and how to improve. Like, for example, now we can grow vegetables in space. I know you have seen the astronauts eating their lettuce. And we can also use microbes. And this is, as you know, we have microbes inside of us, a lot of microbes inside of us that are good for us. So we want to make sure they remain good. We want to make sure that we can use microbes to produce things like yogurt. If you don't know, your yogurt is produced by microbes, and they're also very important in the production of bread and other things. So we want to make sure that they're good for us and they remain good. So that's when NASA and the different technologies and applications we develop are good for. The other big issue in space, particularly outside this magnetic ball protecting the Earth, is the space radiation. And outside the field, the magnetic field, this type of radiation is very aggressive, very, very strong. Many of these so-called particles are very, very fast and carry a lot of energy. Every time one of these particles hits something, can have very bad effects, even on electronics. If we were to be hit by as you can see on the lower right, that's what is called a solar storm. That's the sun, and that huge thing is a solar storm. This was in 2011, 2012. It did not hit our planet. If it had done that, we might have issues with our satellites. Effects on our GPS, on our phones, and our Wi-Fi. A lot of things could get fried, literally, because it's the amount of radiation. So we need to know what this type of particles can do to biology before we send humans. This is just to show you a lot of the things that happen to humans, and I won't go into details, but we have done a lot of experiments on the International Space Station, even in the shuttle era, even with the Russian cosmonauts, the NASA astronauts, and the European astronauts as well. So we know what could happen within this magnetic field that we're protected, but we don't know what happens outside. NASA has had many programs, and this is just NASA. We know that there are other programs out there, but I'm focusing on NASA. We had many programs to study life, to study living organisms, and the most famous ones, of course, are the space shuttles until 2011, International Space Station that is still ongoing. And we hope, as you have heard in previous presentation, is that we have that famous lunar gateway, which is going to allow us to work as a hub, as a station between Earth, Moon, and then later to Mars, of course. And this is all part of Artemis. Some other new program that started not that many years ago in 2006 are these famous CubeSats. So CubeSats are small satellites. Cube is because it's a little cube. And these cubes are 10 by 10 by 10 centimeters. You all have seen these boxes containing Kleenex, the small ones. That's a CubeSat, and that's equivalent to like 1 U. So these little satellites are known for their size, and they come in all shapes and forms, funny enough. On the left, you can see some of the different sizes. In the middle, some examples. You can see on top left there, on the top left, some little ones. Those are 1 U. So these are very small boxes. Our mission is like the one in the middle. It's a 6 U. It's like 6 little cubes put together. And on the right side, you have all the missions that have used CubeSats, these small satellites, to send biology to space. All of them, again, within what is called lowered orbit, within this protection of the magnetic field. And we have studied a few things. You know, we have studied the effects of microgravity on bacteria and how antibiotics have an effect. As I told you before, unfortunately, many of these bacteria become aggressive. So we need to know if antibiotics still work, or do we need to increase the dose of antibiotics? Other experiments we have done is we have used fungi. One of them is Saccharomyces cerevisiae. You might not know its name. That's their scientific name. You call it maybe like baking yeast or like baker's yeast. It's what is used to make bread, your pizza dough, what is used to make even for adults. You know, you have wine and beer, to make yogurt. You can make many things. Actually, nowadays, it's probably one of the most used organisms in scientific laboratories. It's actually being used to make gasoline, to make biofuels, to make plastics, to even make tires. You can make tires out of biology. It's amazing. Or medicine. So we use a lot of these organisms, but they're all within, again, the lower orbits of our Earth-Moon location. And you can see some examples here. You can have all sizes. Can you see on the top left and at the bottom in the middle? Look at the size of those little satellites. They're very limited in what they can do. For the most part, they're used for radio to send signals or to send information. On the bottom left, you have the first CubeSat sent by Guatemala. It's called Quetzal-1. And then on the bottom right, you have Marco. Marco, it was the first. There were 2 of them. There were twin CubeSats. They were sent to the Mars orbit together with a bigger mission. And you can see the picture was taken by one of those CubeSats. So why is Marco important? It was the first mission to use these little satellites in deep space. We're talking about Mars now. So it took a while to get there, took these images, sent some information back and forward with the Mars lander, and then went back to Earth. So it fulfilled its mission. And many of the things that were learned from a mission like Marco, and by the way, the Marco twin satellites were called Marco A and Marco B. And if you're all in all have seen the movies, have you seen the movie WALL-E? One of them was named Wally, and the other one was named Eve. So they were Wally and Eve. Those were their nicknames. And they allow us to test many of the instruments of the engineering staff that will go into Artemis 1, that will go into our mission. So Artemis 1, that's a big rocket. I mean, you guys heard from DSLS folks. You also heard about Orion. So this is the next big thing, you know, the NASA thing. And if you follow space news, you know that we're testing a lot of things. Actually, very recently, I think last week we tested the rockets and how if they're working well. You know, NASA is known for testing everything before we fly. So this is the biggest rocket ever. It's bigger than those used in the Apollo era, and this would allow us, you know, with this force to go to escape the lunar lower orbit, to escape the momentum with the force to escape into deep space and go to Mars and back to the Moon, etc. Now, you guys heard about Orion, right? So you know Orion goes pretty much on the top of the spacecraft, on top of these Artemis missions. Right underneath Orion, years ago, NASA realized they have a space to send smaller missions. And they decided to go with CubeSats, and they're actually going with 13 CubeSats. And you can see the photos at the bottom of how big this, you can see the humans down there. You can see how big this ring is. And inside this ring, also, you see the video on top there. There will be the different CubeSats will be, each of them will be kicked out, at different times. They will never see each other again. Again, space is humongous, they will never see each other again. And every one of these missions has its own objective. And you can see some of those missions here. I don't know if you guys have heard about this. This collaboration, of course, between NASA, universities in the United States, institutions in Italy, in Japan, and also some companies. And some of them are going to study looking for water or ice on the moon. Other ones will do some heliophysics, meaning studies of the sun, or even testing new propulsion, being able to move using water. And then we have Argo Moon. The Argo Moon is a super camera that will hopefully allow us to take very cool pictures of these satellites when they come out of this ring underneath Orion. So BioSentinel, our mission, right? So BioSentinel, again, like I told you, is the first mission of its kind. It's the first deep space CubeSat that will carry biology. So it was built for two reasons. Number one, it was built as a tool that can be used for something else later, maybe to carry something else that is not yeast, maybe to carry bacteria, maybe to carry something cooler than that. It can also be used as a platform to be placed in the International Space Station, which we're doing, to be put on the moon, which will happen in the future, or to be put on the Lunar Gateway, or just lower orbit. I mean, it's just another platform. And then the second main objective is would allow us to know what happens to biology at the level of radiation in space. So again, it's flying on Artemis 1. And FY22, if you don't know, means fiscal year 22, which anywhere between October 1st, 2021 until the end of September next year. So we'll be flying during that time frame, and we'll be flying for a minimum of 6 months. And we're gonna be like millions and millions and millions of kilometers or miles away from the Earth. So we need to send all the information via telemetry. So we send all these coded ones and zeros using the Deep Space Network, and then we get all the data, and then we play with the data back on Earth and realize what to do with it. Again, we're using yeast, and if you don't know yeast, it's down there on the bottom left. That's a yeast, and on the bottom right we have our so-called yeastronaut. It's our yeast astronaut. And so what we do is, like as I told you, yeast has been used in many laboratories. I actually did my doctoral and postdoctoral work using yeast, or a big part of it using yeast. So I know a lot about it. And what we do is we play with the genetics, we play with the DNA to modify to be useful for our particular purpose to be sent to space. And you might ask, why do we use yeast? I don't know if you ever have seen yeast in the kitchen. Yeast comes in these very small packages, right? These yellow packages, or it can be also in like a little mass that you buy to make your pizzas or your bread. So I'm saying this because you can dry yeast. And why is that important? Is because a mission like this takes a long time to prepare. So we need to put the yeast inside this special plastics inside this satellite. And it's going to take months and months until we actually launch into space and be activated into space. So we need to make sure that it remains viable. If you were to send this yeast in like liquid or in another form, it just will not survive. Remember, these are living cells, and we want to keep them alive. So we dry them. And we know everything about the genetics of the yeast. Now let's talk about a little bit of the satellite. So this is the satellite. Again, I told you this is like a small shoebox. You can put boots in there. And I'll show you at the end of the presentation some stuff I have here to give you an idea. I just want you to pay attention to everything that is inside this little CubeSat, which is actually its own spacecraft, and you will see why. And just imagine everything we're putting in there. And at the end, I'll show you on the video the size of this instrument, so you know how amazing it is to put all these little instruments in there. Inside the spacecraft, you have what we call the biosensors right there in the middle. That little cube fun thing with the green color in the middle. That's what the biology is. And outside the biology, outside that section, you have a lot of other stuff. So you power this satellite using the sun. Of course, you need batteries, so we charge all the batteries. Then how do we know where we are? We use what is called a star tracker. It's a super camera that takes pictures of a space, and it uses this information to locate a star, so you know exactly where you are located in space, or to a very good degree where you are. Then at the bottom right, you have that light blue propulsion system. We're actually using a cold gas, and this is not used. We're not like a rocket, so we're not going to go like super fast speed. But this allows us to regulate how we move after we detach from the ring after Orion. Because as you know, it comes, it rotates, it goes around like a little crazy. So we need to use a system to control our movement. We also have all the brains and all the computers. We have a series of sensors because every time that we need to charge the batteries, we need to point the solar panels to the sun. But every time we need to send information to the Earth, we need to point the antennas to the Earth. So you have all these very cool systems inside. Now, this is what's inside. Inside that biosensor payload, you see at the bottom left, you have the little G cells. They're very tiny, again. These are like 20 times smaller than human cells, to give you an idea. This is in micrometers, these microns, very small. It's like what? 1,000,000 times or more smaller than 1 centimeter, or a meter, sorry. Then you have the fluidic cards. So we actually put the yeast inside these fluidic cards. We dry them in there. Then we put a bunch of electronics, a very cool lights around them that allows us to look at what happens to the biology. Then we put this into what is called a manifold. A manifold is just something that allows you to distribute, to guide fluid, to like liquids inside. So we can actually activate or rehydrate, add liquid inside each card at specific time points throughout the 6 months of the mission. And then you assemble these manifolds with all the bags containing the liquids, the reagents, the nutrients inside the 4U. So it's a 4, again, it's like a 10 by 20 by 20 centimeters. And I have exactly what I'm showing you later. And then you put this inside the spacecraft. Now, I pointed out on the green circle on the bottom left, this unit will fly, of course, to deep space as part of the Artemis 1 mission. But also, we're going to put the exact same box on the International Space Station. So we can get information from the radiation outside the magnetosphere, outside the magnetic ball, but also the information inside, very close to our planet, where the radiation is not as bad, but we have microgravity, so it's a perfect control. And we also have our ground controls that we have in some glorified rotisserie that allows us to kind of simulate microgravity. This is a microfluidic system. I won't bother you, but we pretty much have a lot of lights. We have of these fluidic cards, we have 18 fluidic cards. Each fluidic card has 16 little wells, so 16 little holes, which means that we can do 16 experiments inside each fluidic card. If you were to multiply it in your head, we're talking about almost 300 of those wells. So we can play a lot with the conditions and multiple time points. This has never done before. The last mission using fluidic cards only had like 48, I believe. So it's a lot more. And then these lights, once you put liquid in there, the light goes through this well, through these holes, and the yeast starts growing with this media. And then on the other side, you have a detector. So you have something that senses the amount of light and gives you information of how the cells, how the yeast is doing. And of course, the goal is, as you can imagine, throughout the months of the mission, the more the biology is there, the more radiation it gets. So we want to have an idea of what happens over time to that biology, so we can activate these fluidic cards, these little cassettes, and they have an idea of what's going on. Here is just complicated. It's just to give you an idea. Again, remember size and the instruments in there. There are a lot of little valves. There are a lot of pumps, a lot of bubble traps. So all this system has been designed, has evolved. I mean, it has improved from previous generation of CubeSats. And all this goes into that small box again. This allows us to control the liquids. We can actually control the temperature, which is pretty cool. Now, I have been very lucky that as part of this mission, I worked with radiation before. I mean, that radiation that you guys heard that you get when you go to the hospital, you break something, or you go to the dentist. So some similar, just stronger. So there are special facilities that you can go and irradiate your samples with very high energy. These are called particle accelerators, and we have used those to test our biology. In addition to the nutrients, to this liquid that we have, that we add to the yeast inside these fluidic cards, we also have what is called a metabolic dye. It's just a little dye that changes color from blue to pink. And this change allows you to follow how active the cells are. So the worse the cells are, so the more radiation, the more damage they receive, they take longer to change these. And you can see on the top right what that means. It just takes longer. You see on the right, these ones, the ones that have 10, 20, 30, that means a lot more radiation than 0, 2.5, and 5. And you see it's taking longer. So we can have an idea of how long they take to respond to the damage caused by the radiation, gives an idea to extrapolate, to try to compare to what could happen to humans in the near future. Finally, I have just a couple of slides. It's just to show you what our goals, very ambitious goals. As you know, I told you we're going to the ISS for microgravity control. We're going to deep space as part of BioSentinel on Artemis 1. Then we really want to go to the lunar surface, because if you don't know, the Moon and Mars have different gravity. You know, here on Earth we have what is called 1G, one gravity. In space, in free space, is microgravity, so it's pretty much no gravity. Then on the Moon is like 0.17, so it's like a fifth of the gravity. And on Mars is pretty much a third of the gravity. So you have all these variations, and we have no idea what will happen. Some little changes can have an effect, or they might not, but we need that information for future experiments, future missions. And of course, ideally, we want to go to the gateway once it's up there, but that's many years from now. So again, I really like this. You can see on the bottom right, these are 2 CubeSats that were released from the International Space Station. Those are 3Us. Again, I remember 1U is a little box of 10 centimeters by 10 centimeters by 10 centimeters. So why are CubeSats good for science? Just being small, as you can imagine, they're cheaper. I wouldn't say super cheap, because some missions are not cheap, but you can get very creative. It has been used by many universities, even high schools are working on these little CubeSats to learn more about space, to learn more about radio and how GPS and how Wi-Fi works. You might have heard SpaceX, the SpaceX company, sending a lot of these little cubes up to space to get internet around the world. So there are a lot of technologies that can be used for this. So it's a very good education vehicle that can be used all around the world. Guatemala has sent, Peru has sent, Brazil, even many countries have sent their own little satellites to do their own studies. And to put a presence, also remember, like everybody wants to go to space. You want to say, I put El Salvador in space. I'm very proud of that, etc. This is it. This is a picture of my native Peru. This was taken in the mountains of Peru. That's our solar system, as you can see in that great picture. That's my email if you want to call them, if you have any questions. And that's all I have. I want to show you, I'm gonna stop sharing so I can show you something. So remember, you guys can see me now? Yes, cool. So let me show you what I mean. I told you we have these fluidic cards, right?
Yeah, we're not seeing you yet. Mr. Natura, can we spotlight him?
Yes, now we can.
Okay. So remember I told you these fluidic cards? This is one of them. So I told you we have 16 little circles in there, right? So we have like in total like 300 of those little circles. So we actually put the yeast, we put them inside these tiny circles, and then we dry them in here, and then we put a lot of electronics around them, and then we have these manifolds. So we have 2 of these, right? So that's 9 cards, and each card is going to look like something like this, or wrong side, with the electronic. That's where the lights are located, and on the other side, you have the sensors to detect that light. And you have a lot of little, like all the valves and you know, the mixing chambers. So we have 2 of these. Now, all these is going to fit in this little box. This is my hand. So this little box is what we call the biosensor. This is flying to the International Space Station. And what's flying on deep space, I don't have the model with me right now, it's just a little bit taller. But imagine all the technology, everything I told you fits in this little box. And this will be the first of its kind. We hope that we can have multiple missions. And I think that's all I have. So I'll take any questions you guys have any. Thank you.
All right. Thank you. So let's start with the questions. But before we start, let me also show you that this Dr. Sergio Santamaria also shared the CubeSats, a 1U. This is a 1U. Can you guys see me?
Yes.
Yeah. So this is it's like the size of 2 of your fists. That's how small they are. Okay. They're tiny. Okay. Let's begin our Q&A session.
Okay, so it looks like Stephanie has had her hand up. So if you want to go ahead and unmute yourself, we can get your question
It's
answered.
a meet for this one. Yeah. What does it feel like going in space?
What does it feel like going in space?
Yeah.
For me or the G?
Huh?
For me, for a human, or for the little G cells?
No. Like, can we breathe in space?
How does it feel like working on a space mission, you mean?
Yeah. About that.
I mean, it's
We're
super
gonna
cool.
go to a program, right?
So you know, I love working at NASA. It's super cool. I don't want to be an astronaut, that's for sure, because I know what happens, what could happen.
Okay.
But a lot of people would love to go to space. You know, you guys can all be astronauts if you really wanted to. And with time, we'll get better. It's just, that's one part of the space biology field. We want to know what could happen to biology. You know, if we want to go to the moon or to Mars, we need to be better at many different things. So I think we're putting our little contribution as part of the Artemis program to learn more and hopefully do more complicated experiments and to send our astronauts safely to space.
Okay, it looks like Jose has his hand up. So if you want to go ahead and unmute yourself.
Why are we sending yeets up into the space? What's the purpose of sending those up into space?
That's a perfect question, Jose. So, you know, I get asked that question a lot. And a lot of people ask me, why you don't send like, you know, I don't know, rats, monkeys, or like something different, right? There are many things you can send. There are a lot of things that have been sent to space. However, yeast gives you some advantages. You know what the genome is? The genome is all you have inside your DNA, right? So we know everything about the DNA of the yeast. It has been studied for like centuries. It's a very well-known microbe. And you can dry it. That's very important. You can dry. You can dry many organisms as well, but you can dry this organism. Something that you cannot do with rats, something that you cannot do with monkeys, something you cannot do with even with worms. If we could send something better, more closer to humans, we would. It's just we were not there yet. Something very important that I did not mention is like amazingly, the cells inside us as humans and the cells in yeast are very similar in the small level inside the cell, inside the way, especially the way they repair the damage caused by radiation. So it's what is called a model organism. So it's a perfect model for this type of mission. You can dry it. It's similar to humans. You know all the genetics, all the DNA. So it's a very useful tool. That's the reason why.
Okay. Xavier, looks like you have your hand up. Go ahead and unmute.
So, one question. Do you guys have moon dust? And what do you eat for lunch? And how do you get internet?
In space, I hope.
Those are all good questions.
We do have lunar samples. Those are particularly located in Johnson Space Center in Houston. So they were collected many years ago. And what they do is they keep them in. I have been there. I actually did as part of my doctoral studies. I went to Johnson Space Center to do what is called a rotation. I spent some time in the laboratory doing radiation work, and they're kept in these special rooms, because you want to make sure there is the right humidity and whatnot. Regarding lunar dust per se, what is used more commonly is what is called simulant. So we know what's in lunar dust. So we know all the chemicals, all the little components, and we can try to replicate. So you can replicate. You can even buy it online. And I'm not saying go buy it right now, but you can buy it online. And what people do with lunar dust or lunar, dirt is to see, can you grow plants using lunar dust? Can you, and not just for that, for Mars as well. We don't have those samples yet, but people are using again, simulants, right? To something similar. Then you can also expose some organisms, including yeast, including flies, to lunar dust, because it has been seen that it could be not that good for you if you were to eat it, for example. Now, how do astronauts get Wi-Fi? Just like we do. They use a special satellites, special radios. It's not as great as ours, but they do have internet. Now, if you want to know, there's some CubeSats that are being used for new technologies now. They're using lasers to communicate with Earth or between each other. They're using now, I show you that our little spacecraft has solar panels. Some of those satellites actually have a solar panel and an antenna combined. So the antenna is a solar panel. So it's a very cool technology just to use it. And what do they eat? I mean, they eat a little of everything. You can just Google food on the International Space Station, and these guys nowadays they're eating vegetables, because they're growing vegetables on the station. They're also a lot of their food is dry, of course, because it's easier to maintain. But yeah, I mean, besides, of course, the fact that they're floating all the time, they have access to a lot of the amenities that we do here.
Oh, wait, one more question. I just thought about it. I always see pictures of people in space and I don't see their rockets. Where are their rockets?
The rockets don't get there. Have you ever seen one of those launches by these commercial companies like SpaceX that it comes back to the ground? Like, they fly, and then at some point they separate, and then the engine comes back. So once the rocket gets to certain momentum, the bigger the rocket, the bigger the chemicals, the fuel, the farther away they can go, right? So they start going up, then they separate. And once they reach that momentum, that force, they don't need the rocket anymore. So you don't see those rockets. You only see the tripulation, the little capsules like Orion attaching to the International Space Station. The rockets come back to Earth most of the time.
Okay, we're going to do one last question.
See. Okay, Ariel, from Ms. Muller's class, go ahead and unmute yourself.
I have wanted to ask this question for a lot of days, but how do astronauts get to eat when they're in space, and what is the moon made of?
What was the last part? How do they eat, and what's the last part?
When do they eat when they're going to space?
So the astronauts, they actually have a very, very strict schedule. So they have all their hours pretty much programmed. They do have some free time. And when they do free time, that's when they take the nice pictures and they go around and so on. But they have specific times that they have to eat, not just to eat, they have to exercise. Because I told you that you lose muscle and you lose bone. So they need to exercise to maintain the good muscle and good bone. what do they eat? A little bit of everything. I mean, for the most part, it's a lot of have you seen when you get those mayonnaise little containers, you know, little size containers, something like that, you know, they get to eat, you know, their carrot, their purees, like mashed potatoes kind of stuff. They do get some good stuff sometimes, though. They can get, you know, a good meat, but everything dry for the most part. Many times, for example, they get their juices in dry, like I don't know, like you get your little tang or fruit juice, and then they add water into it. Then they mix it and then they drink it. And sometimes they play with it. You can find some videos of the astronauts eating, and nowadays the big changer has been these new instruments, these new machines that allow them to grow vegetables. So they literally are growing vegetables and they're eating the vegetables. I remember the first time that I heard this, they were told not to eat too much, but they, you know, they tried anyways.
Thank you. Okay. Yes, Mr. Martinez.
Okay, let's see. So now I would like for us to take a screenshot. Remember, this is a photo with our special speaker. Amazing work that he shared with us. Okay, this is where everyone opens up their camera. Mr. Natividad, Ms. Martinez, is there a way to bring Dr. Sergio Santamaria into the whole grid? Right now, I'm viewing him on his own.
Let's see, go up in the right on the top and it should say gallery.
Yeah, I just clicked on gallery and I still don't see him in the gallery.
Let's see.
Yeah, he's the only one I don't see. I see him on his own.
I can screenshot him on mine. He's right in the center of ours.
Okay, okay. Why don't you do that then? Let's do it.
Okay,
Okay, everyone. Ariana, you want to open up your camera? Everybody ready?
I have all my stuff. All right, smile. Say cheese. 1, 2, 3. Cool. All right. Gotcha.
We got it.
All right. Well, thank you, Dr. Sergio Santamaria. I'm really proud of all the work that the BioSentinel team has done and all the scientific work that you've helped us develop and research. I think that it's going to be an incredible mission for human exploration, being part of the Advanced Exploration Systems Division. This is one of the missions that are very important to us. Okay.
Thank you very much. Anytime. It's pretty cool.
So now what I want to do is I want to give me 1 second. I want to invite you to come back tomorrow, because remember that. Give me 1 second. Remember that tomorrow we have another great speaker. So tomorrow we have Dr. Jessica Audrey-Lee, and she's going to be telling us all about the work that she's doing, microbes in space. It's going to be somewhat similar, but she's working on a different project. So remember why we're doing this. We're doing this because of you, okay? You guys, all of you are very special. Did everybody do your homework? I forgot to ask. Raise your hand if you did. Okay, and don't forget to do your homework today. Remember, we need you to get really good grades. We need you to listen to your teacher, your parents, be incredible community members of our community, okay? Do well in everything that you do, because we're waiting for you. We, Dr. Sergio Santamaria and I, we need you to come help us. We need you to go to college, get really good grades. And when you're in college, remember, you can come in, do internships with us and work on some of our projects. And once you graduate, you can come and work for us and get paid for your work. Okay, so everybody gonna come in and help us? We really need you to do that, okay? So thanks again. Thank you, Dr. Sergio Santamaria. This was an awesome talk. I'm really happy to hear all the great work that you've done. So we'll see you again tomorrow. We're gonna go ahead and end this session. And don't forget to come back tomorrow, everyone. Bye-bye.
Thank you, everyone.